Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss an important topic which is very interesting, that is entropy. Right? Entropy. We discuss first entropy in the light of reversible processes. Remember, we have already discussed reversible and irreversible processes. In reversible process, we said the process is reversible if the system and surroundings can be brought back to their initial states, right? And we also have discussed that uh, in reversible processes, heat rejection and absorption takes place at constant temperature, and temperature is changed by means of adiabatic processes, right? And reversible process is actually an idealization. All natural processes are irreversible processes that we have discussed. So entropy is very interesting and very important and very abstract concept. So I request you to follow my instruction very keenly and be very attentive in this lecture. So we have discussed zeroth law of thermodynamics, of thermodynamics. We have discussed first law of thermodynamics. Zeroth law of thermodynamics is related to the concept of temperature, right? You know, it helps us to define the concept of temperature. Similarly, the first law of thermodynamics is related or allows us to define the concept of internal energy. Zeroth law allows us to define the concept of temperature. First law of thermodynamics is related to the concept of internal energy, which we denote by U. And you also know that temperature and internal energy both are state variables. Now in this lecture, we will show that second law of thermodynamics in this lecture and the following lectures. Maybe I cannot conclude this in this lecture. So in this lecture and the following lectures, we will conclude or show that second law of thermodynamics is related to a thermodynamic variable called entropy, which we denote by S. We will show that this entropy is also a state function, right? And we will also show that this entropy is used to express the second law of thermodynamics quantitatively, right? We start by considering a Carnot cycle, right? Let me use the next page. Remember the Carnot cycle. So this is my Carnot cycle. You know it, I have discussed it in detail. I'm just referring to it because I need it. Now this cycle includes 4 steps, you know that. I label the points, it is rough. So let me name this point 1. This is point 2. This is point 3. And this is point 4. This is Carnot cycle roughly. So you know, in the first step of this cycle, we have isothermal expansion, then we have adiabatic expansion, then we have isothermal compression, then we have adiabatic compression. So we have 2 adiabatic processes taking place, one expansion and one compression, and 2 isothermal processes taking place, one isothermal expansion and second isothermal compression. We also know that in isothermal expansion, the system is in thermal contact with the hot reservoir at temperature TH, and in isothermal compression, the system is in thermal equilibrium with cold reservoir at temperature TC. In isothermal expansion, heat absorption takes place. In isothermal compression, heat rejection takes place. And in adiabatic processes, temperature change takes place of the system, right? So this much you know, and you also know that when we go in this cycle, we have already discussed that in work and PV diagram concept. When we discussed that lecture, work and PV diagram, we already know that if in PV diagram we go in clockwise loop, right? When we go in clockwise loop, what happens? The network done by the gas is the area enclosed, and that is equal to the heat absorbed. But if you go in the closed path in anti-clockwise, counterclockwise sense like this, then net work is done on the system, and that is equal to this area enclosed, and that is equal to heat rejected by the system, right? I repeat, in clockwise loop, net work is done by the system, and that is equal to the enclosed area under the loop, and that is equal to the heat absorbed by the system. And if we go in anti-clockwise fashion or counterclockwise fashion in the loop in PV diagram, then net work is done on the system, and that is equal to the area enclosed in the loop, and that is also equal to the heat rejected by the system to the surroundings, right? Now coming back to Carnot cycle, when we talk of Carnot cycle, we discuss heat engine. So we are going in the clockwise fashion, right? And we know also that if we go in counterclockwise fashion in this same cycle, then we are talking of refrigerator, not engine, right? Now for Carnot cycle, we know we can write, we already discussed that QC, which we have written in modulus by QH is TC by TH. What is QC? You know these terms. Still, I tell you, TC is the absolute temperature of cold reservoir. TH is the absolute temperature of hot reservoir, right? What is QH? QH is amount of heat absorbed by the system from the hot reservoir. It's heat absorbed, write it simply. It is heat absorbed, heat absorbed. So C modulus is, I write heat rejected. Now we have taken QC under mod because we have used the convention that heat rejected is negative, heat absorbed is positive. So here we are taking only the magnitude. So mod of QC, that is amount of heat rejected to the amount of heat absorbed, is TC by TH, right? We have shown that. So I can discard this absolute value notation. I write it just QC, right? And then I have to remember if it is negative, heat is rejected, and if it is positive, then heat is absorbed. So we disregard or discard the absolute value notation, but we keep in mind that in the process, whether the Carnot cycle is carried out clockwise as an engine or counterclockwise as a refrigerator, QC and QH and QC always have opposite sign. I repeat, this is just for Carnot cycle when we talk of engine. Now we want to take counterclockwise situation as well into consideration. When we go in the cycle in counterclockwise sense, then we are talking of refrigerator, not engine. In clockwise sense, it is engine. Now I write it this way. I write QC by TC is equal to QH by TH. QC by TC is equal to QH by TH. I can write QC by TC plus QH by TH is equal to 0. You can say that I have written it QC by TC is equal to, this is QC by TC is equal to QH by TH. This is 0 because for refrigerator, QH is negative and QC is positive. And for this engine, when I go in the Carnot cycle in clockwise sense, QC is negative. When QC is negative, this term and this term will cancel out. Let me name this equation, equation 1. Don't get confused. I'm saying here in case of engine, we are taking heat because we are using the heat convention, heat absorbed is positive, heat rejected is negative. So in case of engine, my QC is negative, so this sum is going to become 0. But in case of refrigerator, QC will be positive, QH will be negative. So that's why I said whether we talk in terms of engine, in Carnot cycle, or in terms of refrigerator, this QC and QH always have opposite sign. So therefore we can write QC by TC plus QH by TH is equal to 0. Let me here use for an engine, this is minus. For refrigerator, QH is minus. Got it? So this equation, I will write equation 1 states that the sum of the algebraic quantities Q by T is 0 for a Carnot cycle. This is important. Sum of algebraic quantities, heat over absolute temperature. Algebraic quantities because you have to take the sign convention into consideration when you use this equation. As I said, in case of refrigerator, we are moving in counterclockwise sense. Their QH is negative, QC is positive. In case of engine, when we go in the Carnot cycle in clockwise sense, QH is positive, QC is negative. So these are algebraic quantities, right? So their sum is 0 for Carnot cycle. Now our next step is we want to generalize equation 1. So I write, we want to generalize equation 1. That is, sum of these algebraic quantities is 0. We want to generalize equation 1 to any reversible cycle, to any reversible cycle, not just a Carnot cycle, not just a Carnot cycle. So we want to generalize this equation. We have justified that it is true for Carnot cycle. I want to generalize that this equation is true for any reversible cycle, right? To do this, We approximate any reversible path by an assembly of Carnot cycles. Repeat, we approximate. To do this, for generalization, we approximate any reversible cycle, any reversible cycle as an assembly of Carnot cycles, as an assembly of Carnot cycles. Now we proceed in that direction. How to approximate any reversible cycle as an assembly of Carnot cycles. So I draw a figure. I will draw first this figure, then I will explain it. This is my PV diagram. Which color to use? Okay. Let me make 2 more. 3 more. Now in black, this is a reversible cycle. Any arbitrary reversible cycle, right? What is this, these red ones? This is a family of isotherms. Remember, isotherm is that curve in PV diagram along which temperature stays constant. So each curve, each isotherm will have its own temperature. Now, these isotherms will have some temperature difference. So we have superimposed a reversible cycle, an arbitrary reversible cycle in black on a series or family of isotherms, right? Now what is our job? I remind you, I said we want to generalize this equation first for any reversible cycle, not just a Carnot cycle. To do that, we need to approximate any reversible cycle as an assembly of Carnot cycles. Now, I have taken a reversible cycle, which is shown in black in PV diagram, and I have superimposed it on a family of isotherms. Next, what I do, I connect these isotherms by adiabatic paths. See how. So let me make one more isotherm first. So I have to cover it full. Just one more isotherm. This is one more or two more, right? Let me use some other color. Now see what I do. I connect these isotherms by adiabatic paths. This color. This one and this one. This one and this one. This one. Let me make it more color. I will use another color to make it clear. I will use this color. Blue is better. So this like this. I connect these isotherms by adiabatic paths. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, and 2. Now focus. These blue lines, these blue curves are what? Adiabatic paths. Now see, compare it with this Carnot cycle. Carnot cycle is first, it comprises of two isotherms. This one and this one, they are isotherms. And another color, red one. These two curves are what? They are adiabatic paths. Adiabatic paths. So it's one isotherm, it's another isotherm, then they are connected by two adiabatic paths. Same is here. See, these two are isotherms and these blue ones are adiabatic paths. These two red lines are two isotherms. These are connected by adiabatic paths. That means this is, I will encircle it, this is a Carnot cycle. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, right? And again, another Carnot cycle, another Carnot cycle. That means I have constructed a series of Carnot cycles. I have constructed a series of Carnot cycles or family of Carnot cycles, right? Now follow the argument. Now we have an arbitrary reversible cycle. We want to approximate it by an assembly of Carnot cycles. So we have constructed a series of Carnot cycles. Now, important is there is one important thing here. Traversing the individual Carnot cycles in sequence. I should write it. Important. What is important? Let me write it. This color. Important is traversing the individual Carnot cycles. Let me name this figure. Figure 2. Let this be figure 1. Traversing the individual Carnot cycles in figure 2 in sequence is exactly equivalent exactly equivalent in terms of heat transferred and work done to traversing the jagged sequence of isotherms and adiabatic lines that approximates the actual cycle, that approximates the actual cycle. I repeat it. I'm saying traversing the individual Carnot cycles in sequence in figure 2 is exactly equivalent in terms of heat transfer and work done to traversing the jagged sequence of isotherms and adiabatic lines that approximates the actual cycle. See, my actual cycle is in black. Now I have approximated it. I am telling, instead of going this path, this reversible cycle, I can go along jagged sequence of isotherms and adiabatic lines. That is this. Let me use another color. It is becoming messy, but I have to explain it. I think I will use the pointer. See, what is a jagged sequence? First, I go along this isothermal expansion, for example. Then I go along adiabatic expansion, then isothermal expansion, then adiabatic path, then isothermal expansion, then adiabatic path, isothermal expansion, then adiabatic path, then isothermal expansion, then adiabatic path, isothermal, adiabatic, isotherm, adiabatic, isotherm. This will become like this. So let me make it on another side. This was, let me get my pen back. Where's my pen? This is my pen. Understand this. This is my actual path. So I'm saying I go this way. Right, roughly. So this red is what? It is the, which I'm seeing, jagged sequence of isotherms and adiabatic lines. This jagged sequence of isotherms and adiabatic line. So we're approximating that curve in terms of this curve, red, black one in terms of red one. So we are saying that whether we go along this jagged sequence of isotherms and the adiabatic lines, which are approximating the actual cycle, that is equivalent, exactly equivalent to traversing the individual Carnot cycle. So we go along first Carnot cycle, then second Carnot cycle, then third, fourth, fifth, and so on in sequence. In terms of what? In terms of work done and heat transferred. In Carnot cycle, only two things are important. That's heat transferred and work done, right? Whether heat is transferred or work is done. So I'm saying if I go along series of Carnot cycles, what is the meaning of equivalent? Same amount of heat and work done will occur. Heat and work will be same for the jagged sequence of isotherms and adiabatic lines and the series of Carnot cycles in sequence, right? Got it? I repeat, I am saying that work and heat for jagged sequence of isotherms and adiabatic lines and series of Carnot cycles in succession will be same for both these things. That's why we are saying they are exactly equivalent. But there is one thing which may confuse you when you think about it. How is that possible? How? Think about it at home. About it at home. I will give you a hint. Two Carnot cycles, adjacent Carnot cycles, have one isotherm in common. Two Carnot cycles have two adjacent Carnot cycles have a common isotherm, and there will be two traversals in opposite directions, right? Along the common isotherm, there will be two traversals, but those two traversals will be in opposite directions, which will lead to the cancellation in the region of overlap as far as the heat transfer and work done is concerned, right? I'm saying that this is possible because two Carnot cycles adjacent ones have one isotherm in common, and you have to traverse that isotherm twice in opposite directions, and that will lead to the cancellation of the heat transfer and work done in the region of overlap. So that will make this statement correct, right? We take it as a fact, you can check it. So therefore we can write, since we are saying that this jagged path is uh, equivalent to the series of Carnot cycles, and for Carnot cycle we said that this sum is zero, algebraic sum is zero, so therefore same will be true for the jagged path, because they are equivalent in terms of heat and work. So I can write, therefore we can write for the isothermal adiabatic sequence of lines in figure 2, this figure 2, summation q by t is equal to 0, right? One more important thing, now see, we are approximating the reversible cycle in black with this jagged sequence of isotherms and adiabatic lines. Now this will become more exact if these isotherms are close to each other. That, in other words, means if the temperature difference between two adjacent isotherms is made smaller and smaller, this jagged sequence of isotherms and adiabatic paths will be better approximation for the reversible path, right? So I can write, in the limit or in the limit of infinitesimal temperature differences between the isotherms, infinitesimal temperature differences between the isotherms of figure 2, this is my figure 2, can write dq by t closed integral is 0. This sum will become integral. So closed circle on the integral indicates what? That integral is evaluated for complete traversal of the cycle, starting and ending at the same arbitrary point of the cycle, right? So I name this equation 2. This was my equation 1. This is my equation 2. We have now made temperature difference between two adjacent isotherms infinitely small, and we have generalized this sum to this, but our cycle is to be traversed in closed way. starting and ending at the same arbitrary point of the cycle, right? So this indicates that must be knowing, or I have already said it, that the idea of state variable, this equation is saying that the integral of a variable around a closed path in this coordinate system PV diagram, this is saying integral of this quantity over a closed path in the coordinate system PV diagram is 0. That, in other words, means that the value of the variable at a point depends only on the coordinates of the point and not at all on the path by which we arrived at that point. Such a variable is called what? State variable. So what I repeat here, I'm saying that if we have a quantity whose integral around any closed path in a coordinate system is 0, then the value of that quantity at a point depends only on the coordinates of the point and not at all on the path by which we arrived at that point. Now, such a variable is often called as state variable, meaning that it has a value that is characteristic only of the state of the system, regardless of how that state was arrived at. So equation 2 is such an integral, and therefore dq by t must be a differential change in a state variable. We call this new variable as entropy. We denote it as entropy. We denote it by S. So ds is dq by t. ds is dq by t. This is my 3. This was second. So equation second becomes closed integral ds is equal to 0. This is my 4. This now ds, so closed integral ds is equal to 0. Now you can see the SI unit of this new quantity entropy is SI unit of entropy is joule per Kelvin, right? Now, the essential point of these equations 2, 3, and 4, 2, 3, and 4 is that although dq is not an exact differential, that means heat is not a state function, but dq by t is exact differential, that means this quantity is a state function, right? Now this was the infinitesimal change in this entropy, the finite change in entropy between two any states, the change in entropy between any two states I and F is then Delta S, change in entropy in final state. SF is the entropy in final state, minus SI, entropy in initial state, is simply I to F. We have to integrate these infinite small changes, ds, which can be written as I to F dq by t. But this is valid, we establish it only for reversible process. Because this integral is to be evaluated over any reversible path connecting these two states, right? I summarize the lecture. First, I said that second law of thermodynamics is related to a quantity called entropy, which is state variable. Like first law is connected with internal energy, zeroth law is connected with temperature. Then we took the example of Carnot cycle. We said this sum for Carnot cycle, algebraic sum of these quantities q by t is 0. Then we generalized it to any reversible cycle. How? We approximated an arbitrary reversible cycle as an assembly of Carnot cycles. So we were able to write this equation. Then we said, since this is 0 over a closed path, this the integral of dq by dt, this must be an infinitesimal difference of some state function called entropy, right? And for finite change, we wrote this equation. But this is valid only for reversible process. This is all for today. Thank you. Assalamu alaikum.